Chapter 6 Homework for Sharing Stress. Homework 6.1 4 millimeters thick. So from side view, we have 4 millimeters thick, 3 of them boards and 10 centimeter wide. So if you look from the top, it will be 10 centimeter wide, 4 millimeter. Side view, top view are connected together by two parallel rows of uniformly distributed nails separated by distance delta. So this is side view. You have nails, and the distance between the nails would be delta. Okay, that will be between the top and the middle, between the middle and the bottom, that will be nails. And the two parallel rows. So from the side view, you only see a row, but if you look from the top, you would see the two separate rows. To form a beam that is subject to vertical shear of 1000 newtons. So this downward transverse force 1000 newton. Okay, so if you look at the top, the force would be here going downward. Knowing the maximum allowed shearing force for each of the nail is 200 newton. So you can imagine each of the nail can handle certain force, and we said it's 200 newton. Greater than 200 newton, the nail may bend or even break or fracture. So we want you to determine the largest longitudinal separation data between neighboring nails. Largest longitudinal separation, this data. As you can imagine, if this data is too large, then the horizontal shearing force may be larger than the 200 newton. So it cannot be too large. And we want you to determine, to calculate the maximum allowable distance. Maximum allowable distance data between the neighboring nails. Okay, so again, this is side view. Each of this board is 4 centimeters thick, and from the top view is 10 centimeter wide. And each of the board is long, and the three of the board are connected by two parallel. Actually, if you consider the ones from the bottom, then that will be four, but two rows, okay, of nails. And we know each of the nail can handle 200 newton of shearing force, while the vertically applied, the transverse applied shearing force is 1000 newton. Okay, so to do this problem, I draw the schematics again here. Again, this is the left one is side view, 3 boards, each of them 4 centimeters thick. And then if you look from the top, it will be just one board and 3 of them stacked up together, and there will be 2 parallel row of nails, and the distance between neighboring nails, we call it delta. Okay, delta here or delta here. And as we said, each of the board is 4 centimeters thick, 10 centimeter wide, and the length can be very, very long. Okay, so from the cross-section view, if we do a normal cross-section for, you would get something like this. Still 3 layer, top, middle, bottom, top, middle, bottom. But then if you look at this cross-section, we would have 2 rows, one here, one here. Okay, and in order to use our equations for transverse shear, we would need to calculate the first moment. And as we said in the class, the first moment Q is calculated always from the normal cross section for the beam. So you can choose your element of interest, and let's choose it to be the top board, and we choose this cross section. And then this red dash line represents the interface of interest. And along this interface, the shearing force matters. Or put another way, the shearing force in this interface would have the tendency to bend these nails or cut through the nails. Okay, so this will be our interface of interest, and the red dashed section from cross section would be we will use that to calculate the first moment or the Q value. And from the top, you can choose our element to be something like this, spanning through one set of nail. Okay, so let's look at still the cross section. The first moment, the Q value for the section element of interest, as we said, is you calculate that from the cross section view, and the Q, as we said, first moment would be Y bar times A. A would be the area, cross-section area for the element of interest, and Y bar would be the distance from the center of gravity for that element to the neutral surface. So for our chosen element of interest, as you can see, the Y bar would be from center of gravity to the overall center of gravity, and or centroid, and that distance would be the same as 4 centimeter, and the cross-section area for the element would just be the thickness times width, which would be 4 centimeter times 10 centimeter. As a result, the first moment would be 160 centimeter to the power of 3, or cubic centimeter. And then we also need to calculate the moment of inertia, and that's always for the entire normal cross section, And for this entire normal cross section, it will be BH to the power of 3 divided by 12, and the B would be parallel to the bending moment, and that value would be 10, the width here, while H would be from here to here, which is 4 centimeter times 3. Okay, and we plug the number in, we would get the value to be 1440 centimeter to the power of 4. Okay, again, moment of inertia would have the unit of meter or centimeter to the power of 4. First moment would have the unit of centimeter to the power of 3, or meter to the power of 3. Okay, so then the total shearing force, specifically the horizontal shearing force between the chosen element and the remaining of the beam along the interface of interest, we said it will be this red dashed line. For the chosen section, we said it must not be larger than the total shearing force that could be allowed for 2 nails, one here, within the chosen section. So delta H is VQ over Y times delta X should be equal to or smaller than the 2 times the allowable shearing force for each of the nail. Okay, so this is what we have. Delta H equals VQ over I times delta X. It should be smaller than 2 times the allowable shearing force for each of the nail. Again, V would be the transverse or vertical shear force. Q would be the first moment for the element of interest, and we said Q corresponds to this red dashed section in the cross-section view. I is moment of inertia for the entire normal cross-section, and we said it should be smaller than 2 times of the allowable shearing force for each of the nail. Therefore, the distance between neighboring nail delta should just be the delta X here, and it should be equal to or smaller than I goes up to 2 times F nail times I moment of inertia divided by VQ. And as a result, delta, the interdistance between the nail should be 2 times each of the nail. We said it can handle 200 Newton of shearing force. I, we said it's 1440 centimeter to the power of 3. V, we said is 1000 Newton, and Q is 160 centimeter cube. As a result, you plug in the number, you can get the answer. Okay, and that concludes homework 6.1. Homework 6.2. For uniform square box beam, we are looking at the cross section, a box beam, square shaped, with outer edge of 5 inch, from here to here 5 inch, from here to here 5 inch, and wall thickness of 0.5 inch, so 0.5 inch, 0.5 inch, okay? And the loading shown in the center, 2 KIPS, or 2,000 pound of force at the center for the DE beam. Consider cross section C prime, and we want you to calculate the largest average shearing stress in that section, in that cross section, and the shearing stress at the point X, the shearing stress at the point X in the cross section of the box beam. Of course, these are not drawing in scale. This is side view. This is normal cross section view. Okay. To do this, the first step what we can do is we can calculate the moment of inertia for the entire normal cross section. It's a prismatic beam with a box beam with a square cross section. So the moment of inertia for this structure would be the outer minus inner. B1, H1 are for the outer dimension, B2, H2 are for the inner dimension. And here, because it's a square cross section with uniform wall thickness, so it will be for outer, it would be just a 5 inch to the power of 4. For the inner, it would be 5 minus 0.5 minus 0.5, it will be 4 inch to the power of 4. And plug the number in, you get the moment of inertia for the entire normal cross section would be 30.75 inch to the power of 4. Okay. Then the average shearing stress from the what we learned in this class, tau average shearing stress due to transverse shear V would be VQ over IT. Again, I would be the moment of inertia for the entire normal cross section. T would be the interface width, okay? And V would be the transverse shear force or vertical shear force. Q would be the first moment for the element that we chose. Okay, for part A, we want to know the maximum average shearing stress, and for such a cross section, from what we learned, I would be constant, and the maximum average shear would be the Q reaches maximum, because V term would be constant, I term would be constant, and the maximum would reach when T is small and when Q is large. And T, if we look at it, and because of symmetry, it will be uniform from here to here, and another uniform from here to here. So T would be this plus this, or 0.5 plus 0.51 inch, and the Q, we want Q to reach maximum, and the Q reach again, this is box beam, Q reaches maximum when we consider the element of this shaded red, okay, when this shaded red, dark red, when the bottom line reaches the so-called neutral surface. So in this case, the chosen element, if we chose this one, then the Q, the first moment for the chosen kind of like a half link, would be Q for O minus QI, outer minus inner. Outer would be for this 2.5 by 5 inch, and the inner would be from here to here times from here to here. Okay, and the first moment would be y bar times area for outer, y bar times area for inner. Again, outer would be for this 2.5 by 5, inner is 2 by 4. Okay, so for the outer, the center of gravity to this neutral surface would just be the half of the distance from here to here, which is 2.5 inch divided by 2. That gives the y bar for the outer dimension. The outer area would just be here 2.5 times from here to here of 5. Okay, this gives us the QO for outer part first moment, and inner part first moment, which is for this part, it will be y bar would be from the center of gravity from here to here, and from the top to the center would be 2.5 minus the thickness 0.5, which is 2 divided by 2. That gives us the y bar, and the area would be 2 times from here to here would be 4. And if we plug the number in, we will get the first moment for this C-shaped or half link from the top would be 7.625 inch to the power of 3. Okay. The width, as we said, if this is our interface of interest, the total width for the interface of interest would be 0.5 plus another 0.5, it will be 1 inch. Therefore, the maximum average shearing stress is occurring along the neutral surface, and tau would be VQ over I. And what is our V? From statics, if we have 2,000 pound of force of P in the center, because of the symmetry D left, E right, the shearing force would just be the same as the reaction force at D and E. It will be half of you applied. It will be 1,000 Newton. So the average shearing stress would be VQ over IT, which is 1,000 pound times Q. For the C link, we got it from previous slide, 7.625 inch to the power of 3 divided by I we calculate the molar inertia for the entire cross section is 30.75 inch to the power of 4, and T we said is 1 inch from here. As a result, we would get a number in the unit of pound force per square inch, or PSI. Okay. Finally, for part B, we want to calculate the average shearing stress at X interface. Okay. Then for the second part, the element of interest chosen would be again this rectangular red shaded bar, and its first moment would be y bar times area. And what is y bar? Y bar would be from here to here 2.5 minus half of the thickness, 2.5 minus 0.5 divided by 2. That gives a y bar in the unit of inch times area. Area would be thickness 0.5 times length 5 inch, and we plug the number in, you would get 5.625 inch. Okay, so the total width for the interface of interest, if we make the cut here, it will be 0.5 on the left, 0.5 on the right. It will be 1 inch. So the average shearing stress at the point X interface would be VQ over IT. V we said the same as 1,000 pound of force. Q we got 5.625 inch to the power of 3, I 30.75 inch to the power of 4, and thickness would be 1 inch, and you would get the unit of pound per square inch of PSI. Okay. Homework 6.3. A beam DE, a prismatic beam, same cross section of length L, sometimes you call it a span L, and the rectangular cross section with width of B and height, vertically height of H. And we said this would be a narrow beam, which means the height would be greater than 4 times the width. Okay, such a simply supported prismatic beam with rectangular cross-section carries a uniformly distributed load W. We have W uniformly distributed. So we want you to determine the condition in terms of the relationship between length of span L and the beam cross-section height H. So the relationship between L, length or span for the beam, and the height, the H, for the cross-section of the beam, for this normal cross-section of the beam. When the maximum shearing stress, tau max, and the maximum axial normal stress, sigma m, equal each other, or something like this. Tau m would be the maximum average shearing stress, and sigma m would be the maximum axial normal stress. When these two values are the same, we want you to derive mathematically the relationship between length of span L and the cross-section height H. Okay, so this is our problem. How do we solve this problem? Well, this is a problem that we see before in chapter 5, and simply supported the beam, and because of the uniformly distributed load, we can have the reaction at left side, at D side would be 0.5 WL. Distributed load times length, RE would be because of the symmetry, the reaction force at E side would be the same value, 0.5 WL, and both are pointing upward. So this would be the free body diagram for the entire DE beam. And from chapter 5, we can get the so-called shear diagram. We would have shear that changes linearly with location, and the internal shear would be 0 at the center and reaching 0.5 WL at the D side and reaching minus 0.5 WL at E side. Okay, that is a shear diagram. And also from previous chapter 5, we can also get the moment diagram. We get something, a parabolic shape, and the local slope corresponds to the absolute internal shear value, which means at the center, we would have 0 slope or 0 internal shear, while the slope is maximum at the 2 ends. Okay? So let's consider what is our axial normal stress, axial normal stress, maximum axial normal stress. From what we learned before, axial normal stress would be mc over I, moment, internal bending moment, and C would be the maximum dimension. One can be away from the neutral surface. I would be the entire cross-section moment of inertia. And for sigma to reach maximum for the entire beam, essentially we request the C dimension to go to maximum, as well as the moment to reach maximum, considering this is a prismatic beam, which means the I, the moment of inertia, would be the same. So based on our shear diagram, the maximum moment would occurring at D side or the E side. If we consider D side, the absolute value would be 0.125 WL square. Okay, or 1/8 WL square. That will be the maximum internal bending moment on this beam. And the maximum dimension one can be away for such a rectangular cross-section beam would just be half of the cross-section height of 0.5 h. So plug these numbers in, and the moment inertia for such a rectangle cross-section would be 1/12 bh to the power of 3. So if we reorganize, this is 1/8, this is 1/2, and totally it's 1/16, and this 12 goes to the numerator. We would have 12/16, that gives us 3, after simplification, gives us 3/4, and W we keep, L square we keep, and B we keep, H and H to the power of 3, so we have H to the power of 2. So this value would be the maximum axial normal stress for this entire prismatic beam under such a uniformly distributed load. Okay, so we have our simply supported beam, prismatic beam with uniformly distributed load, and from chapter 5 we said we will have shear diagram, we will have bending moment diagram. The shear diagram is a straight line and reaching 0 at the beam center, and the moment diagram is a parabolic curve. In previous slide we obtained the so-called maximum axial normal stress within the entire beam by considering the maximum moment. Now let's consider the maximum shearing stress, average shearing stress. Also from this chapter, we said for a narrow rectangular beam, we said what do we mean by narrow? For a rectangular beam, if the height is 4 times of the width of base, or h is 4b or larger than 4b, then the maximum shearing stress can be approximated as 3 times the shearing vertical shear over 2 times the normal cross-section area. Okay, so that's what we learned earlier in chapter 5 for a narrow cross-section, rectangular cross-section beam. Now, for such a simply supported beam, the maximum shear is occurring either at D side or at E side, and that value would be 0.5 WL, 0.5 WL. So you plug the number in, the maximum shearing stress that we can obtain would be 3 times 0.5 WL over 2A. A would be the normal cross-section area, which is B times H. So simplify, 3 we keep 1/2, and 2 it will be 1/4 WL over BH. Okay, so this would be our maximum shearing stress when we consider the shear diagram. Now finally, let's make them the same. When the maximum axial normal stress and maximum shearing stress are the same value, which means sigma max equals tau max, we would have sigma max from previous would be 3WL squared over 4BH squared equals tau max, which is 3WL over 4BH. And of course, 3 and 3 cancel, 4 and 4 cancel, B and B cancel, L and L squared become L, H squared and H become H, and essentially what we are going to have would be L length over H would be equal to 1. Okay, the length or the span for the beam, the distance from D to E would be equal to the height, cross-section height. Okay, what this tells us is when this condition is satisfied, we are talking about a very, very short beam. The span, the length is the same as cross-section height for such a rectangular narrow beam. And as a result, for typical beams that are typically much longer than the cross-section height, the transverse shearing stress, even the maximum value would be much smaller than the axial normal stress, and as a result, the transverse shearing stress term is often neglected for practical long beams. Okay. Homework 6.4. A box beam made by gluing together four pieces of wood planks, wood plank, one on the left, one on the right, one on top, one at the bottom. Again, you are looking at a normal cross section for the box beam. The beam is a cross section, looks like a rectangular open box and coming out from the screen towards you. Okay, so a box beam is made by gluing four pieces of wood planks. The cross-section dimension is shown as before, like 5 cm here, 10 cm here, 5 cm here, 2.5 cm, 10, 2.5 cm. So if the allowable average shearing stress in the glued is that this is the glued interface, this is the glued interface, this is another glued interface, this is another glued interface. So if the allowable average shearing stress in the glued joints or interface is 200 kilopascal, we want you to calculate the largest allowable vertical or transverse shearing force that can be applied to the beam. Okay, largest allowable vertical shearing force in the beam or that can be applied to the beam. Okay, in the plane of symmetry. So from the cross section, we can easily choose the element of interest to be this element or this piece on the top, okay, and it's glued on the left and on the right to the remaining of the beam. So again, this is right shaded part is our chosen element of interest. And we set the allowable shearing force per unit length. The allowable shearing force per unit length for the glued interface on either side would be stress, allowable stress, times the width for that interface. So, okay, we are trying to calculate shearing force per unit length. For the glued interface on either the left or on the right would be the stress times a length, because we are talking about the force per unit length, okay, which is Newton per meter, and this one is stress has a unit of Pascal, Newton per meter square, times length, it will be Newton meter. It will be the same, okay. Then, for this chosen element of interest, to use what we learned in this chapter, we quite often have to calculate so-called first moment for the chosen element. And the first element is always calculated from the normal cross-section. And this is our shaded red is our normal cross-section. Q first moment would be y bar times A. A would be the area for the cross-section area for that element that we choose, and y bar would be the center of gravity from that element to the neutral surface or centroid for the entire cross section. So in this case, the neutral surface, because of the symmetry, definitely would be in the center, and the y bar would be the center for this shaded area. To the center, it will be half of this term, which is 5, plus half of 5 centimeter, 2.5. It will be 7.5 centimeter. That will be our y bar. And the normal cross-section area for the element of interest would just be 5 centimeter times 10 centimeter. So you plug the number in and you will get the first moment for the element that we choose will be 375 centimeter to the power of 3. Okay, that will be our first moment. And then to get information about sharing force sharing stress and axial, we need to get the moment of inertia I for the entire normal cross section, and that is considered this whole thing, box beam. And because of its rectangular shape, we can write it as 1/12 B1 H1 3 to the power of 3 minus 1/12 times B2 H2 to the power of 3. B1 and H1 represent the width and the height for the outer rectangle, while B2 and H2 represent the width and height for the inner rectangle. So if we plug the number in, B1 would be 10 plus 2.5 plus 2.5 would be 15 centimeter, and H1 would be 5 plus 10 plus 5 would be 20 centimeter, but H1 to the power of 3 would be, don't forget. And then for B2 would be inside, this is 10 centimeter for base, and H2 is also 10 centimeter, but for H2 it's to the power of 3. Okay, we plug the number in and we would get the approximate moment of inertia for this entire normal cross section would be 9,167 centimeter to the power of 4. Okay. So from previous slide, we get some geometric information such as the first moment for the element that we choose, as well as the moment of inertia for this entire cross section. And we said horizontal shear flow or shear force per unit length based on the equation small q would be VQ over I times delta x over delta x, or just VQ over I. Shear flow or shearing force per unit length for the chosen element should satisfy shearing force should satisfy because it's held back by both left side and the right side. It has to be shearing stress, allowable shearing stress times the weight, but then we need 2 because it got pulled back by both the left side and the right side. Therefore, the vertical and transverse shear, which is V value satisfied, V has to be equal to or smaller than 2 tau average times 5 centimeter times I moment of inertia divided by the first moment Q. Okay, and the allowable stress we said is 200 kilopascal. So 2 times 200 kilo 10 to the power of 3 Pascal. 5 centimeter, we write it down, and I we said is 9,167 centimeter to the power of 4. Okay, and we can convert centimeter into meter, 5 centimeter 0.05 meter, and centimeter to the power of 4 we would transform into 10 to the power of minus 8 meter to the power of 4. Okay, because 1 centimeter is 10 to the power of minus 2, and the whole thing to the power of 4 would be 10 to the power of minus 8 meter to the power of 4. And you plug the number in, we said Q is 375 centimeter cube, and 1 centimeter cube would be 10 to the power of minus 6 meter cube, and you would get the final answer for the vertical transverse shear, assuming that the vertical transverse shear in the plane of symmetry, and we would know its maximum value that can be applied. Okay. Finally, for 6.4, there is another approach, or so-called alternative solution. We don't have to calculate so-called shear flow, but let's just use also another factor that we learned in this chapter 6, which is average shearing stress in the interface of interest. We said interface interest would be here, And here in the interface of interest, tau average would be VQ over IT. Okay, V again would be transverse shear, Q would be first moment for the element of interest, I would be moment of inertia for this entire cross section, and T would be the width for the total interface that separates the chosen element from the remaining of the beam. So as a result, the transverse load V would be equal to tau average times IT over Q. And the tau, we said average has to be smaller than our allowable stress, and IT we keep. So as a result, the transverse shear has to be equal to or smaller than allowable stress 200 kilo 10 to the power 3 Pascal times I we calculated. It's 9,167 centimeter to the power 4 or meter to the power 4, but times 10 to the minus 8. And T would be the width of that total interface would be 5 centimeter here, 5 centimeter here. You add it up, 10 centimeter times 10 to the minus 2 meter. And finally, first moment we calculated for the red shaded area. And as a result, we should be able to get the same exact answer. Okay, and the transverse or vertical shear that can be applied has to be equal to or smaller than this value when we consider the limitation of shearing stress for the interface of interest.